I have a voltage going that direction. There's some voltage here. From positive to negative, that would be negative voltage. My electric, we'll do that here in the other direction. So I have a positive voltage going this way, because I'm going from low to high. My electric field is going that way. If I got a positive negative side of the negative side of the battery, I have an electric field going from the positive to the negative. That electric field is equal to the force times the force divided by the charge of, I guess I should say, that electric field, probably better worded, the force on a charge would be equal to that charge times the electric field. I like that one better. I also know that for the most part, this electric field is relatively constant throughout the wire. And so that's equal to the charge times whatever the voltage is divided by the length. We'll just call it L. And I want to differentiate my V's here. This voltage, I'll make that a capital V, and this one, let's add a little serif to it to give some sense of lowercase. I thought we could do this without looking at notes, but I'm gonna have to look at my notes because there are a lot of bad paths to go down. All right, so let's connect some of the stuff we did with what I've just written up on the board. See if we can figure out what we have control over and what we don't. I know current is the change in it's the amount of charge that flows by a particular spot in a certain amount of time. If I'm assuming electron flow, or assume that whatever's flowing, there's some average charge. This Q here, that is the charge of one particle times however many particles I have. Sorry. So Q is basically charge of the charge carrier. And N is number of charge carriers. Well, the number of charge carriers that are going to be passing by that particular spot, we're going to create one more variable here. Well, this is the charge carrier density. And it's just the number of charges per unit volume, or the number of charge carriers. I do want to differentiate between charge and charge carriers. That I have an atom with a bunch of charges on it, but if those charges aren't moving, then I don't care about them. These are only the charges that are actually, that will be moving. So if I look at this particular segment right there, my volume of that little segment is, well, I've got some length here and then a cross-sectional area. So my volume is just the length times whatever my cross-sectional area is. And, well, actually, I'm going to rewrite that as delta x instead of L. It'll make life a little bit simpler in a moment. So N It's just my charge carrier density times my volume, which is A delta x. So this becomes Q little n A delta x over delta t. And I have a delta x over delta t. What is that?
Displacement?
Not divided by time.
Velocity?
Speed.
Speed.
It's just the drift speed. So this is just Q in A times whatever my drift speed is. Now, it still doesn't help us with what we can control and what we can't. So let's explore that speed just a little bit more. Speed is distance divided by time. But if you think about it, this particle comes in, it's going to hit something and then bounce. On average, the initial velocity, well, it's just as likely to hit something going this way as it is to go that way. On average, my initial velocity, this symbol for average, is equal to 0. So if I think about what my final velocity is, it's equal to the initial velocity plus acceleration times time. So the velocity is on average just acceleration times time. Acceleration, actually, what's Newton's second law? So A is F divided by M, so this becomes F over M times T. And the force acting on it, well, that's just the charge times the electric field. We can do it in terms of voltage, so that becomes Q E. I feel like I'm suddenly going to go in a circle here. Reintroducing time. Keep it like that. And let's plug into here. So we end up with Q in A times Q E over M T. Now that time there, that's the time it goes from hitting one thing to hitting the next thing. This is the time that the electron is in between hitting, so this has a name, and I want to make sure I say it the right thing. I want to be nice if I wrote it down somewhere. So, I wrote it down as the average time between hitting anything. So this is the average time. There's a name that I'm pointing on right now. There's something known as the mean free path. And the mean free path is the distance that it travels, that a particle travels between hitting things. And this is the time it takes, the time of that, average time of that. And so I'm just going to use the letter tau to represent it. So I have these two charges here. So I have Q squared in A E over M times tau. And now let's just be specific. Let's throw electrons into it. If electrons are flowing, This is again equal to my current. This is equal to E squared, charge of the electron, times the charge carrier density, times the area of the wire, times the electric field over M tau. Oh, that's mass of the electron. Let's think about what we have control of here. If I pick a wire, well, charge of the electron is set, mass of the electron is set as far as we're concerned. The charge carrier density here and tau is dependent upon the material. These are material dependent. A is dependent upon the wire itself. Not the material, but how the construction, geometry of the wire. And the electric field is dependent upon the voltage that we choose. We actually have control over that. So when I pick a material, well, I've got these constants of material there. I can basically, if I pick a material, I can calculate these. The combination of these four things is for a particular material. I can find it experimentally. And so E squared in tau over ME, that is known, the symbol used is sigma, and this is known as the conductivity. Two of them are constants and two of them are material dependent. And that's a tau, not an I. So I've now simplified. My current is just sigma A E. If I divide both sides by A, I get I over A. This is a side note, not where I want to go ultimately, but this current per area. So I have current flowing through here divided by the amount of area. This is known as a current density, usually symbolized by the letter J. This is the current density. And I think of this as the Joe equation. The J is equal to sigma E, and E equals like Joe. All right, so back from over here. I know my electric field is just equal to my voltage divided by length. So I'm going to go back to L again. So if I is equal to, the other board. We're coming close to the end. It's getting there. My current flowing through that wire is equal to sigma A delta V over L. Now physicists, for whatever reason, decided they didn't like conductivity as the feature they wanted to use. They would rather look at the negative side of it. And they said, you know, if that's conductivity, which is an indication of how easy it is for charges to flow, we want to look at how hard it is for charges to flow. So they made up a new thing. The symbol they used is a rho. And this is known as resistivity. So I pop that in here, and so now my current is equal to A delta V over rho L. I'm going to solve for delta V because I know where I'm heading on this one. And that's equal to rho L over A times I. And at this point, physicists decided, you know what? I like that, except I want to call it something different. Of course. The resistivity times the length divided by the cross-sectional area is known as resistance. And so the equation now simplifies down into the voltage is equal to the current times the resistance. And this gives us incredible power. I have a battery, sorry, wrong symbol, a resistor, this is a resistor, and it is hooked to a battery. Let's make this a 3 ohm resistor and a 12 volt battery. Volts usually not characterized by the letter in there. 12 volt battery. I don't know what the actual potential is at either side of that battery, but I do know the difference. That's my negative side, my positive side. I know whatever this is 12 volts higher than that. So I'm just going to pretend that's 0 for the moment, and that's 12. No matter what path I take, this should be 0. So if I go across in that direction, just conceptually, I should lose 12 volts. If I go around this way, I should lose 12 volts. No matter what path I take to get from there to there, the voltage is still the same. Flash back to when we defined voltage and I had the different electric potentials, and no matter which path we took, it was still the same difference. So if I'm going to lose 12 volts going across here, so if my potential difference across the battery is negative 12 volts in the direction of the current flow, I can now figure out what the current is. Because I know my potential difference there is got to be equal to the current times my resistance. And so it would be 4 amperes. Or volts per ohm. This is omega, it's a capital omega. And it represents an ohm. Named after? Oh. Yes. Now sometimes physicists like looking at things, the flip side of it. For instance, if took a thermodynamics course and we didn't deal with the temperature so much as the reciprocal of the temperature. There is a reciprocal of resistance, and the symbol for the unit for the 1 over R, that unit, would be a 1 over ohm, or an upside down capital omega, and that is known as the mho. And the only reason I bring this up is if you're playing Scrabble or Words with Friends or one of the other word games, this is a legitimate word. The other one that I've managed to use once in a Scrabble type game. Later on, we will deal with the unit of the Henry. There is a reciprocal Henry called the, here now, it is a legitimate word. To my knowledge, those are the only 2 units that you can just write backwards and it's still a legitimate unit. I've never actually heard anybody pronounce this. I pronounce it Irna, but no idea how it's really pronounced. Just like I've never actually heard anybody pronounce that one, but I'm still assuming it's pronounced Mo or Mo. Yeah, Mo sounds better. Anyway, one last bit of trivia here, and actually this is slightly more than trivia. This right here is known as Ohm's law. And I want to point out one last thing. We still have only used one physics equation in this entire course so far. Coulomb's law is the only physics equation we have done. All the rest of it is math and definitions. This is Coulomb's law, just it's been distorted, kind of like creating orcs from elves. But Coulomb's law is buried in there. Anyway, I hope you have a wonderful weekend. Look forward to Tuesday's festivities. And there it is. And Daniel, if you figure out when.
Yeah, I'm gonna take it tomorrow.
Okay, so you rescheduled?